So let me say the title for this last presentation is called Weekly, from week, not from week, Supervised Pseudo Label Generation for Construction Vehicle Segmentation. Authors are Wei-Chi Chen, Vijayan Asari, Tam Nguyen, and Honjo Kim.
Hello everyone, my name is Wei-Chi Chen, and today I would like to introduce our work, Weekly Supervised Pseudo Label Generation for Construction Vehicle Segmentation, to everyone. And before I dive into the details, I would like to talk about the problems for semantic segmentation. So the problem is that to prepare annotation for semantic segmentation, it requires a lot of time. And for the example below, we have classification, object detection, and semantic segmentation. For classification, we only need to provide the labels for each images. So in this case, we have a mixer truck and also a roller. However, for object detection, we need to provide a bounding box around our target objects. And that is still considered relatively easy to prepare this kind of annotation. However, for semantic segmentation, we need to carefully provide a polygon annotation around the edge of our target objects. So as you can imagine, this is a really time-consuming process. And imagine if you are preparing a data set with thousands of images. For semantic segmentation, it would take you months to just prepare the data set before you start training. So, and there are many researchers looking for solutions to minimize the cost for semantic segmentation's annotation. So one technique that is commonly used is called the class activation mapping. And we will use the class activation mapping, or CAM, as the pseudo labels to train our semantic segmentation models. And for the CAM techniques, it is commonly used with the classification models. And therefore, we only need to provide the classification labels, and that is relatively easy to do. And because we are now using the classification labels to generate the pseudo labels to train our semantic segmentation, so it is now considered as a weekly supervised learning. And if you look at the image right here, you will see this is a demonstration of how the CAM works. So in order to get the final attention map of the model while making a certain decisions, we will be looking at a certain neuron that is triggered, and we will looking at its weight and use these weights to multiply with the corresponding feature maps. So as you can see, the weights multiplied by the feature maps, and if we sum them all up, we will get a final attention of this model as this model is making a certain decisions. So in this case, the model is actually looking at a dog and then making a corresponding decisions. However, there are certain issues with this kind of CAM techniques. So the CAM could actually generate relatively coarse annotation maps, and that is not fine enough to train a segmentation models. Second of all, because we are training a classification models, the classification models can actually become really smart and just taking shortcuts to make classifications. And if you look at the image below right here, this is one of our model that is with a really high classification accuracy. And if we visualize the attention while the model is making decisions, you will notice that the model only pay attention to the most discriminative features of each class. The model does not need to look at the entire objects in order to make decisions. And therefore, as you can imagine, this is not a good CAM as a pseudo labels to train our segmentation models. And to overcome this, we need to find ways that could encourage our model to pay attention to other foreground regions, not just the most discriminative features. And before I dive into the details of our proposed architectures, we would like to briefly mention our contributions. So we propose a new fusion architectures that outperform its predecessors. And our fusion architectures consist of two different architectures that were also designed to do the same task, to generate pseudo labels for semantic segmentation. And one of them is called the SIM architectures, and the other is the SCCAM architectures. In addition to just fusion two different architectures, we also optimize each architectures so that we will get better performances. And our architectures actually scored at least 9% improvement in the mean IOU score to the AIM dataset that consists of different construction vehicles. And our proposed method, as I mentioned, is a fusion architectures of the two different models. And for the SIM architectures, it consists of a PCM module, which is a pixel correlation module to capture the context information. And the PCM is actually a modification of a self-attention module. And therefore, as you can imagine, the self-attention module actually encourages the model to also consider the context information, because the foreground, the neighbors of the foreground pixels are more likely to also be the foreground pixels. And for the SCCAM architectures, it proposes a subcategory exploration. And for the subcategory exploration, it actually encouraged the model to recognize the differences within the same object class. So if you look at the diagram on the right side, this is actually a label preparation process for the SCCAM architectures. And so let's take the dump trucks, for example. When we will collect all the images that contain dump truck, and then we will fit into a CNN feature extractor, so convert each images into a meaningful features vector. And those feature vectors will be the input of a k-mean clustering to cluster all the dump trucks into smaller classes. And if you visualize the smaller classes, you may discover that the cluster number 1 could be the dump truck that are smaller in the images. And cluster number 2 will be the dump truck that are larger in the images. And the cluster number 3 could be the dump truck that are in specific scenes, for example, in construction scenes, and so on and so forth for other clusters. And if you visualize each clusters, then you will probably have a general idea what features of each clusters has. And that relies on the features that is extracted by the features extractor. And in our original proposal, this is the architectures we originally proposed. And at the bottom region is the SIM architectures, and the upper right region is the SCCAM architectures. As I mentioned, the SIM architectures contains the PCM module that would encourage the model to also look at the neighbor pixels, because they are also more likely to be the foreground pixels that the model missed. Additionally, the model have a smaller scaled input, and the reason using this kind of smaller scaled input is based on their observation. They discovered that if the image becomes smaller, the CAM, the class activation mapping, will actually cover more regions of our foreground target. And they use this smaller scaled input CAM as a ground truth to guide the original scale CAM, to encourage the model to also look at the entire region more treated like as the smaller scaled images. So this way, it will also encourage the model to cover more regions for the SIM architectures. And for the SCCAM architectures, at the upper right regions, not only do we have the original class labels, we also have the subclass labels. And for the original class label and subclass labels, we will have two loss functions to calculate loss and make sure the model will also optimized for this subclass classifications. And now we have an improved design of our proposed fusion models. So for the SIM architectures, we actually remove the smaller scale input range. As based on our experiments, we noticed that the observation of CAM covering more regions with smaller scale images is not consistent with the AIM data set. So we removed the smaller scale range for the SIM architectures. Additionally, we also modified the PCM module. So the previously proposed PCM, it only take the fixed amount of feature maps from feature extractors. But now we modify the PCM so that the user can easily define the number of different scaled features is used for the PCM module. And based on our experiments for the AIM dataset, if we change the feature map from 2 to 4 different scales, we actually acquire better performances for the pseudo labels. And for the SCCAM architectures, we modified the training strategy to shorten the training time. And for the training process that I just mentioned, for the SCCAM, because it contains a label preparation process to acquire the sub-cluster labels. So it is actually an iterative training process. And in our experiments, the label preparation and training process will be repeated 3 times. So as I mentioned, when we use a pre-trained CNN feature extractor to acquire the encoded features and then do the k-mean clustering to acquire the subcategory labels, we will start training the model, entire model. And afterward, we will get the model number 1. And for the iteration number 2, we will use the model number 1 as the feature extractor to acquire the subcluster labels and use the newly generated subcluster label to retrain the model again. However, in the original SCCAM implementation, they will start over the training from scratch. However, we reuse the previously trained model from the model number 1 as a starting point. Then therefore, we will be able to reduce the training epochs and also reduce the required training time significantly. Then we will repeat a similar process to use the model number 2 to generate a new set of subcluster labels to train the model again. And similarly, we will use the previously trained model number 2 as a starting point to get the final model number 3 to generate our final pseudo labels. And by using the previous model as a starting point rather than training from scratch, we could reduce the training time significantly. And after we train our model and use that model to generate the pseudo labels, we actually have an extra post-processing step. We will be using the CRF, this conditional random field, to finalize our pseudo labels. And if you look at the image below, the left column, we have our input images. And the middle column is actually the output CAM. As you can see, the attention of the generated pseudo label is still rather coarse. And then we will use the CRF to finalize our pseudo labels as a refined pseudo labels to train our semantic segmentation models. And the CRF will, based on the colors and the distance between the original input images and the given CAM, to make the final pseudo labels for training. As you can see, the result of CRF is significantly better than the original, more coarse CAM. And for the results, we also show the SIM architectures and the SCCAM architectures. And for the pseudo labels, our proposed methods is actually improve at least 9% more significantly. And if we have the pseudo labels and fit into the CRF algorithms, it would generate a refined pseudo labels. And in our case, if we apply the CRF, we could have about a 2.6% improvement in the mean IOU score. However, as you can notice that the mean IOU score for the SIEM architectures and the SCCAM architectures did not improve that much. Is because the generated pseudo labels contains too much of background pixels. And therefore, the CRF will consider those background pixels as the foreground pixel as well. And therefore, the CRF will be making the incorrect results, and therefore results in a decrease in mean IOU score for the SCCAM. And for the SIEM architectures and for the SCCAM, it only improved about 0.1%. And if we use our refined pseudo labels for training a segmentation model, we could actually get a better performances of 74% in mean IOU score. And here are the visualization of of the AIM dataset results. The middle column is the ground truth human annotated labels, and the right column is the prediction of our trained segmentation models. As you can see that the model is actually be able to capture some of the really fine details of the objects. And here are our references. And thank you. This is the end of our presentation.
Well, thank you, Wongyo. Dr. Kim, I think he is connected, so he should be alert to any questions you may have. So any questions for the audience? First, let's check if he's there. Dr. Kim, are you there?
Yeah, I'm here.
Are you there, Dr. Kim? Hi. So let's see who has questions from the audience. Yes, there is one question, Fred.
Thank you very much. This is really interesting, and the performance is really outstanding, actually. How sensitive is the SCCAM to the K selection for K-means, or how do you define the K value?
Okay, thank you for the question, Fred. We have tested several numbers of K. I'm not sure what's the final number K, but I believe it is the 5. And depending on the number of K, the performance could vary in a significant gap. So we rather stick to the number 5, I believe so. But I can share the exact number later. Okay.
Is it like the same K for all classes?
Yes.
Okay. Thank you.
Thank you.
Well, it is 6:30. Thank you, Dr. Kim, for your presentation. It is 6:30 flat, so we are ready for the next event. So thank you very much for attending our technical keynote and plenary talk session. Now we're moving on to the sponsor keynote 2 for the day. So thank you very much. And by the way, thank you, ISARC, for allowing ISARC to be held in Colombia. I'm very grateful with ISARC for this opportunity. I'm sure Colombia needs to have more events like this. And as long as I can help to make it happen, it will happen. All right, thank you.